All right, let's go back to the presentation for about 45 minutes here. And here is just a very handsome list of all the tests that you can possibly perform in order to see whether or not your series converges or diverges. You got your nth term test for divergence. It doesn't do anything for convergence, only for divergence, right? Geometric, very, very easy to use. Ordinarily, it starts at 0 here. If it doesn't start at 0, your sum is going to be a little bit different because you have to figure out your first term. We know it converges if the common ratio, the absolute value that is less than 1, but if it's greater than or equal to 1, it diverges. Integral test, you need to first get yourself a function, which has to be continuous and positive and decreasing, and then you take the integral from 1 to infinity, the improper integral, and see if it converges or diverges, because your series and that improper integral are going to do the same thing. P-series, also very easy, almost as easy as geometric, except for you don't get a sum at the end. So if your P there is bigger than 1, we know that it converges, and if it's between 0 and 1, including 1, it's going to diverge. Here are two comparison tests. Direct comparison test or the limit comparison test, where you're comparing your series to something that you know already converges or diverges. To be convergent, you have to be smaller than a convergent series. To diverge, you have to be bigger than a divergent series. If those inequalities do not hold, you can try the limit comparison test, where, again, you compare it to something favorable. You take the limit of the ratio of those terms, and if that limit is finite and positive, then your two series do the exact same thing. And then finally, we have our alternating series test. Our alternating series, we have an alternator in there, and it doesn't test for divergence. It only tests for convergence, and there's two things to check. The limit of our terms have to go to 0. That's the first thing you want to check. And you want to make sure that the n plus 1th term is smaller than the nth term. This one does have a remainder. Alternating series remainder is always less than or equal to the first neglected term. So if we went up to the 5th term, the remainder is less than or equal to the 6th one, right? And then finally, our ratio test. Here's what our series looks like. I'm going to use it when there's a mixture of things like exponentials, factorials, but if it's a p-series, don't use it. You got a p-series test for that thing. So we know that it converges if I take the ratio, absolute value n plus 1 term over the nth term, it's less than 1. It's like geometric. If that ratio is greater than 1, it diverges. If it's equal to 1, you know absolutely nothing. All right, we're not quite finished yet, or at least you're not quite finished yet, because I've got a handful of examples that I would like you to try. And it combines every single convergence or divergence test that we have learned so far. So I'd like for you, there's not going to be another video for this, write down these series and then check your work in the lesson answers to check to see, are you getting it? Are you able to tell what series test you're supposed to use? Are you using that test appropriately? Are you coming up with the correct conclusion? All right, and so that's going to finish off this lesson on absolute convergence and ratio test, where we are able to determine whether or not a convergence series absolutely or conditionally converges, and then learn this new powerful test, very, very satisfying test called the ratio test, to see if a series converges or diverges.